Hello, my name is Michelle Lee, and I am a senior studying astrophysics and nuclear engineering at the University of California, Berkeley. And today I'll be talking about post-detonation nuclear forensics using fast neutron activation of ubiquitous materials. In this project, I aim to determine an analytic tool for nuclear forensics and security applications by utilizing the fact that a thermonuclear bomb, which is caused by a combination of fission and fusion reactions, can yield a free neutron that peaks at an energy different to that of neutrons produced in a pure fission reaction. This analysis was conducted based on previous experimental work done by Owe Akindele et al. At Lawrence Berkeley National Labs in 2013. I conducted a qualitative and quantitative analysis on the products of neutron irradiation and the measured gamma ray spectra for the 25 different elements the Akindele et al. Group irradiated via the 88-inch cyclotron in LBNL. Utilizing the readily available data on the NMDC and table of radioactive isotopes, I was able to identify the products of four main reactions that follow neutron irradiation, which were N-gamma, N2N, NP, and N-alpha reactions. Utilizing the data table I made here, I was able to extract the peak areas of the various lines from the experimental data, and then use those results to deduce the initial activities and ratios. Depending on the threshold energy of a reaction, the probability of it occurring can vary. For isotopes that can be produced by both 3 and 14 MeV neutrons, I calculated the ratio of initial activities for each isotope to see if a clear ratio can be determined. For reactions with a threshold energy larger than 3 MeV, those reactions can only occur by 14 MeV neutron irradiation, and thus only the identification of such products were deemed necessary. These are two examples of the spectra I will be presenting in my poster. These plots display the energy of the gammas on the x-axis and the number of counts of the corresponding gammas on the y-axis. The plot on the right is nickel, displaying an example of having an N2N reaction creating nickel-57 and an N-deuteron reaction producing cobalt-57 that both have threshold energies that are larger than 3 MeV and thus can only be seen on the 14 MeV spectra data. The plot on the left is of gallium, and because the NP reaction producing zinc-69 isomers and the N-gamma reaction producing gallium-72 both have threshold energies of less than 3 MeV, the ratios of two products were calculated for each neutron energy. Just by looking at the height differences of these peaks, we can expect a rather different ratio for the initial activities of these radioisotopes. This was a brief summary of my project, and additional spectra and details on the analysis will be available on my poster, and I'll be happy to answer any questions during the live conference session. Thank you.